basics. Now today we are going to start with the VBT. That is your valence bond theory. That is your valence bond theory. So what we will do with the help of example, we'll do the valence bond theory. Okay. So in the valence bond theory, there are few things that we get to know. The one is your hybridization, the most important. Okay. Second is the geometry. Okay, we get to know about the geometry. Okay, hybridization, geometry, then magnetism, your magnetic properties. Is it diamagnetic, paramagnetic? What is it? Okay, that also, okay, magnetic property. Okay, so with the help of VBT, we get to know about hybridization, geometry, magnetic property, and all those. Okay, so let us do one example. Okay, we'll do it with the help of example. Okay, now for example, I'll take two examples. Okay, NiCl4. Okay, I'll take NiCl4 2 minus, NiCl4 2 minus, and NiCN4 2 plus. NiCN4. Let us take two examples. NiCN4 2 plus. Okay, now NiCl4 2 minus. Okay, so what we have to do? We have to find out the hybridization according to VBT. Now, how to solve VBT? I want complete focus. Today's lecture very, very important. Okay, we'll try to complete VBT and CFT. Very, very important lecture. Look over here. NiCl4. So what you have to do first, you have to write down the electronic configuration. Then according to the oxidation state, you have to remove the electrons. For example, look over here, nickel. What is the atomic number of nickel? Yes, everyone. What is the atomic number of nickel? Correct, Sarjana? Or what we call surgeon. I remember, surgeon. Okay. So, Kevin, what is the atomic number of nickel? And what is the atomic number of nickel? Jason? Kirtini, please turn on your camera. What is the atomic number of nickel? Correct, it is nothing but 28. So if I write down the electronic configuration, please remember it is 8, so 3d8. So remember like this, 4s2, 3d8. Nickel we have 4s2, 3d8. 4s2, 3d8. Okay, so we have nickel 28, 4s2, 3d8. Yes, and tell me what will be the oxidation state of nickel? Yes, everyone. What will be the oxidation state of nickel? Come on, calculate, Kirtini, calculate oxidation state of nickel. Yes, what will be the oxidation state of nickel? Correct. Nickel is nothing but +2. Nickel is nothing but +2. How did we calculate, Kirtini? How do we calculate oxidation state? What is the oxidation state of nickel? Yes. Jason, what is the oxidation state? Correct. So how do we calculate, Kevin? What is the oxidation state of nickel? So over here, how do we calculate? Kirtini, look over here. If I want to calculate for nickel Cl4, yes, 2 minus. So nickel, I'll take it as X. Correct? I'll take nickel as X. Cl, the charge on Cl is -1. How many Cl do we have, Kirtini? We have 4 Cl. So X -4 -2. Okay, X -4 -2. So obviously goes that side, becomes +2. Yes, -4 goes that side, becomes +4. 4 -2 +2. So we have got, Kirtini, +2. What is the meaning of +2? Plus charge. When do we get plus charge? Jason, Sarjana, and when do we get plus charge on anything? Yes? Kirtini, am I audible? No? When do we get plus charge? Correct. When it loses the electron. When it loses the electron. So simple. You have to remove 2 electrons. So our nickel 2 plus, what will nickel 2 plus become? Nickel 2 plus will be your 4s0 3d8. 4s0 3d8. Now over here, this is where your VBT starts. So you have to draw those orbitals. You have to draw those orbitals. First, I'll start with this nickel 2 plus. Now remember, in the VBT, Jason and Sarjana, you have to go in the order. First 3. then 4, then 5, like that. For example, 3D will come first, then 4S, then 4P, then 4D. Okay, 3D, 1, 2, 3, 4, 5, 4S, 4S, 4P, and 4D. Are you getting it, everyone? Is it clear till over here? We have to go in the order 3D, 4S, 4P, 4D, 4F. Okay, you have to go in the order. Now, over here, how many electrons are there in the D, Kirtini? There are 8 electrons, correct? So what I'll do, 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8. Now, depending upon Jason and Sarjana, depending upon your strong field or weak field ligand, you will pair the ligand. Okay, I will give you the list from strong to weak. Just hold on, let us complete this question. Okay, but for now, remember your Cl is a weak ligand. Your Cl is a weak ligand. Weak ligand does not have power to pair the electron. Simple as that. Okay, so over here, how many ligands we have, everyone? Jason and Sarjana, Kevin, how many ligands we have? We have total number of 4 ligands, correct? We have total number of 4 ligands. Each ligand forms which bond, by the way? Which bond does it form? Covalent, ionic, coordinate. Yes, each ligand forms what bond? Is it covalent bond? Is it ionic bond? Is it coordinate bond? What type of bond is this? Yes, everyone? Come on, tell me. It's in the name. What is the name of chapter? It is in the name, isn't it? It forms, Kirtini, it forms a coordinate bond. And each bond is formed, so 2 electrons are filled in the same orbital. For example, over here 4 ligands are there. That means 8 electrons are there. So that does not mean I'll fill the electrons like this. 1, 2, 3, 4. No, you will not fill the electrons like this because they are forming a bond. So 2 electrons at a time in the same orbital. So over here, Kirtini and Jason, your 4 ligands will fill the bonds like this. 1 ligand, 2 ligand, 3 ligand, and 4th ligand. Are you getting it? Jason, are you getting it? Sarjana, and so over here, where you have put the electrons, simply you have put electrons in this orbital. Okay, you have put electrons in this orbital, and that orbital has, we have used 1s and 1, 2, 3 p orbital. So sp3 hybridization. Are you getting it, everyone? Come on, yes or no? Is it clear? Jason and Sarjana, is it clear? Kevin? Okay, now few things. What is diamagnetic, paramagnetic? Is this diamagnetic or paramagnetic? What you can observe from these boxes? Yes, is it diamagnetic or paramagnetic? Correct, and correct, Sarjana. Kirtini, is it diamagnetic or paramagnetic? Yes. Kevin says dia. Jason says para. Kevin, how do you know something is dia or para? Yes, how do we know something is diamagnetic or paramagnetic? Yes. How do we know something? Okay, this is diamagnetic, this is paramagnetic. How do we know? Yes, correct, Kevin. So, Kevin, over here, these are your unpaired electrons, no? So, Kirtini, how do we know something is diamagnetic or paramagnetic? Diamagnetic means all electron has to be paired. But Kevin, Kirtini, we have the unpaired electron. That means what? Yes, it is sp3 hybridized and it is paramagnetic. Is it clear, Kevin? It is paramagnetic. Correct? It is paramagnetic. Okay. Then next what we have after sp3 hybridization paramagnetics, the magnetic property. Why, Kevin? Acha, yes, you mean. Okay. So the next we have is the magnetic property. What was the formula, Jason? And Sarjana, what was the formula for magnetic moment? Yes, Kirtini, what was the formula for the magnetic moment? Kevin? Root n plus 2. Root n plus 2. And n is number of unpaired electrons. Simple. So from this, Kirtini, 2 unpaired of electrons are there. So 2 plus 2, 4, 4 2 is 8. Are you getting it, everyone? Yes or no? Come on, give me yes or no. Is it clear? Okay. Come on, write it down and done in the chat box. Then I'll go ahead. Come on, write it down and done in the chat box. Come on, write it down and done in the chat box. Write it down and done in the chat box. Jason, Kirtini. Kirtini, are you writing? Show me book and pen in front of camera. Yes, Kirtini, where is book and pen? Show in front of camera. Yes. Then come on, take book and pen and start writing. Do not do it like this. Go, bring book and pen. Ganesh. Ganesh.
Yes, sir.
Kindly drop a message after the lecture to Kirtin is that form. Okay. The first half an hour was not writing anything.
Hello.
Ganesh,
Yeah.
just drop a message to Kirtin's mom and dad after the lecture that for first half an hour, Kirtini was not writing anything. Okay?
Okay. Okay.
No, do not do it. I'll take
Okay,
it.
sir. Yeah.
Done. Okay. Shallow. Let us go ahead. Okay. So, where were we? NiCN4. Now let us do it for NiCN4. Let us do it for NiCN4. Cn is a strong field. Okay. Same thing, same thing, same thing. Okay. One more thing. It should not be 2 plus. It should be 2 minus. It should be 2 minus, isn't it? Minus 1 goes to that side. This should be minus 2. Okay. Now everyone, come on. Let us do this again. So what is the oxidation state? Everything is same over here. Ni2 plus. Yes, Ni2 plus will be what? 4S0, 3D8. But I am showing you now what is the difference between a strong field and a weak field ligand. Look over here, everyone, Jason. The difference between strong and weak field ligand. See, normally I'll draw the box same. 1, 2, 3, 4, 5. This is 3D. Then we have the 4S. Then we have the 4P. Everything same. Okay, everything same. So I'll fill the electron, Jason, Sarjana, I'll fill the electrons 1, 2, 3, 4, 5, 6, 7, 8. 6, 7, 8. Now I have filled the electrons, but this time, Kirtini, Jason, and we have a strong field ligand. So strong ligand will pair this thing. Okay, strong ligand will pair everything. So what will happen? Those will pair. So those will pair. So again, I will 1. Okay, everything will pair. Are you getting it, everyone? Yes or no? Due to strong field that has paired. Okay. Now the ligands, again the 4 ligand, each ligand gives you 2 electrons. So 1, 2, 3 and 4 ligand. So what is the hybridization over here? Yes, everyone in the chat box, what is the hybridization? Yeah, what is the hybridization? Yes, what is the hybridization? Come on, tell me. What will be the hybridization? Correct? Yes, Kevin, Jason, Sarjana. It is not necessary. That is the exact thing why we have this VBT. Look over here. Your hybridization, you have to write it from where does it start. Your first electron, you entered it over here. Your ligand entered it over here. So that will come first. Are you getting it, Sarjana? So we have 1D, 1S and 2P. And this is what exactly our VSEPR failed. VSEPR never considered D as the first orbital. Are you getting it, Sarjana? That is the exact reason your VSEPR failed. And hence we have this VBT. Is it clear, everyone? Come on, give me yes or no. Is it clear? Kirtini, is it clear? Have you written it down now? Come on, write it down, everyone, and done in the chat box. I'll give you the list of strong field and weak field ligand. Kirtini, write it down, please. So will strong ligand, acha, can you explain 1 second? Okay, let us do it 1 second. Let us do it 1 second. Okay, look over here, everyone. If you want, I'll do it. Just a minute. Look over here, everyone. Let's do this 1 second. We are going to do more examples, don't worry. Okay, we are doing NiCN4 2 minus. Okay, first thing, what did we do? We calculated the oxidation state. Correct. So calculation the oxidation state. This is, we have got Ni2 plus. Why, Jason? Because I have NiCN4, correct, 2 minus. So if I calculate the oxidation state, X minus 4 is equal to minus 2, X is equal to plus 2. So oxidation state same, plus 2. So from that we have got 4s0 3d8. Everyone is clear till this step? Jason and Sarjana, Kevin, everyone is clear till this step? Yes? Everyone is clear till this step? Come on, give me yes or no. Yeah. So over here, then we know that we have 4s0 3d8. Now again, Jason, what do? We go in the same order. 3d, 4s, 4p. Okay, I have drawn the 3d orbital. In the 3d, I have put the 3d8. Okay, done. Okay, done. Then we have a strong field ligand. Now, Sarjana, it is not necessary that every time everything will be paired. Okay, what if we have odd number of electrons? Okay, Sarjana, what if we have odd number of electrons? That time it won't pair. Getting my point, Sarjana? If we have odd number of electrons, it won't pair even if it is strong. Okay, like yes, pairing will happen, but one will remain unpaired. Okay, then we have to fill those electrons. Due to strong field ligand, this has moved over here and it has paired. Okay, it has paired and we have got something like this. Okay, now how many ligands we have? And Jason, Kirtini, how many ligands we have? We have the 4 ligand. Each ligand donates 2 electrons in each orbital. So first ligand, second ligand, third ligand, fourth ligand. You have to start filling from the same orbital. Are you getting it? You have to start filling from the first orbital. So, and what we have used? We have used 1d orbital. Okay, we have used 1d orbital, that is over here. 1s orbital, that is over here. And 2p orbital, that is over here. So dsp2 hybridization. Is it clear? And Jason, Sarjana, is it clear? Yes?
So is there a particular reason why there is no electron in the third orbital of 4p? Because while filling, it should be like first everything should be filled and then paired up.
No, 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 no. You have to pair first. See, what happens is your ligand, it does not form directly. What happens is you have a metal. This is what we are going to do in CFT. What happens is you have a metal, okay, in a ground state relaxing. Okay, from beginning you do not have any complex compound. Complex compound we prepare. Okay, so you have a metal, ligand approaches those metal. Okay, so if your strong field ligand is approaching the metal, okay, it is same as like if some strong personality, you are in some event, okay, and some strong personality is coming, okay, what happens, whoever sitting on the first row, automatically they go behind and they sit on the second row, isn't it? Yeah, same thing over here, that if strong ligand is approaching, automatically your electron of the metal gets paired in order to accommodate that strong ligand. Are you getting it? And are you getting it? Yeah, so first pairing happens, then you have to fill the bond, then you have to fill the ligands. Okay, same thing. Is it clear, Sarjana? Sarjana is our strong personality, isn't it? No, you know who is the strong personality? Kevin. He attends every lecture, sleeping on the bed. Yeah, Kevin. What more personality you want? Yeah, Kevin.
No, sir, I'm not sleeping, sir.
So what is it?
I'm sitting on something.
A human being can sit like this also. Oh my God. No, I
Yes,
can
sir.
I can share your screen, but let it be. Can I? Should I?
No, sir, no need, sir.
Should I? Huh? I can share,
No,
like, like there's a trick by which I can show everyone's face, but let it be. Okay.
don't, sir, don't, sir.
Okay. Let it be. Okay. Hmm. So Kevin is our strong personality, or Kevin does some very good yoga. Kevin, please recommend us also that you can sit and sleep in the same position. Bapre. Chalo, write it down, everyone. Write it down and done in the chat box. Kirtini, are you there? Kirtini, did you write it down? Show me the book and pen now. Okay. Chalo, let us go ahead. Yes? Everyone done in the chat box? So that I can go ahead. Done, done. Okay, chalo. Let us go ahead now. After this, come on, write down the list. Okay, write down the list of our strong field and weak field ligand. See, obviously there will be some sort of exceptions. It is not necessary that it will be followed hard and tough. Okay, I'll share all the possible examples with you. No example come outside from that. Okay, all the possible exam I will share it with you. Okay, so some exceptions are there. You can take it from there. Okay, so come on, write down the list. This will be useful for your CFT also. Okay, so the strongest ligand we have is the carbonyl, CO. Then we have CN minus. Okay, then we have EN, that is ethylene diamine. Okay, then we have ammonia, that is NH3. Then we have EDTA. Come on, write it with me. Okay, then
Sir,
after
NH3
EDTA,
is strong or weak ligand, sir?
it is a strong ligand. Okay, depending on the situation. Okay, your NH3 generally act as a strong field ligand.
Okay,
Okay,
sir.
then we have NCS. Okay, then we have water. Then we have C2O42 minus. What is C2O42 minus, everyone? How many of you remember? We have done it in the nomenclature. Yes? Very good, Sarjana. Very good. And yes, Kevin, what is C2O42 minus? Oxalate. Sindhuja, you have come late today. Okay, so here is your list. Here is your list of strong to weak. This is also called as spectrochemical series. It's also called as spectrochemical series. Spectrochemical series. This tells you about the strength of the ligand. Okay, this tells you about the strength of ligand. Okay, this tells you about the strength of ligand. Prashanti, you are not well in every lecture. Yeah. So anyways, okay, you can keep your camera off. Come on, write it down and done in the chat box, everyone. This gives you about the strength of ligand. What is that before H2O? It is NCS, not NC5. It is NCS minus. NCS minus. Okay, so you can consider up to water it acts as a strong field ligand, or up to NCS. Okay, water in some case it acts as a strong, it acts as a weak. Okay, I'll tell you all the examples, don't worry, but write this down. Write this down. Up till EDT everything is 100% strong. Okay. Chalo. Can I give you one example? Will you solve? Will you solve? Okay, let me give you one example. You have to tell me the one more thing. Okay. Now over here, what is the geometry? We did not talk about geometry. Yes. sp3. What is the geometry? NiCl4. Kirtini, what is the geometry for sp3? Yes. Sarjana and Kevin, Jason, what is the sp3 geometry? Yes, Bhuvneshri, Sindhuja. sp3 hybridization, what would be the geometry? Yes, correct. It is tetrahedral. And dsp2, although there are same 4 ligands, okay? dsp2, hence your NiCN4 is square planar. So add it to your list. In the VSEPR, we did not do this because for VSEPR, this does not exist. Okay. dsp2, it is square planar. Come on, write it down. dsp2 is square planar. Okay. Square planar. TD is tetrahedral. Kirtini, not tetragon. It is tetrahedral. Tetrahedral. Okay. Chalo. Let me give you an example. Let us say, okay, what example should I give? Okay, do this. Okay, suppose I have MnCl4 2 minus. Suppose I have MnCl4 2 minus. Come on, you are going to tell me about hybridization, geometry, everything. MnCl4 2 minus. Come on, everyone, write it in your book, and you have to show the book in front of camera. Okay, I'll see all the boxes also. Kirtini, is it clear? Come on, write it, solve it, tell me the hybridization, tell me the geometry, and I am going to look at the books. Kirtini. Come on, solve it. MnCl4. Tell me even the magnetic property. Come on, everyone. Okay, very good. You have calculated the oxidation state, Kirtini. Just a minute, everyone. Just a minute. Very good. Sarjana, please calculate the magnetic moment also. Sarjana, calculate the magnetic moment also with the formula. And just excuse me for a minute. Yes. Bhuvaneshwari got it. SP3. Yes, everyone. Root 35. Very good. Tetragonal. Bhuvaneshwari, not tetragonal. It is tetrahedral. Very good, Jason. Kya baat hai? Perfect. Nice. What have you all eaten today that everyone is giving the correct answer? Okay. Kevin, did you get it? Now show me your books. Show me your books. Show me your books. I'll start it from our surgeon of the group, Sarjana. Okay. Okay. Thank you so much, Sarjana. Kevin, show the book. Have you done it? Acha, doing it. Okay. And okay. Okay. Thank you so much. You can keep it down. Okay. Then Kirtini, did you do it? Show the book. Okay. Nice. Okay. Sindhuja. Okay. Okay. Chalo. Jason, it is fine. I said it is fine. Okay. Thank you so much. Chalo. I hope everyone is clear. No one has doubt now. Wow. I do not even have to solve it. Everyone has got it correct. Nice. Okay. Chalo. Then now tell me. Okay, I'll give you one more example. Cu NH342 plus. Cu NH342 plus. Come on, solve it. Cu NH342 plus. Cu NH342 plus. Cu NH342 plus. Okay, Kirtini. Very good, Sarjana. Hybridization. I want hybridization from everyone. sp2. No, how it can be sp2? We have 4 ligands, no? So it will be in 4 orbitals, not the 3. How did you get dsp2, not sp3? And why not sp3? Jason got it sp3. Okay. 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 Now this is a slight exception. Okay, I did not like it in the last question. Yes, I did not like it. Last question, each and every student got it correct. Yeah, I did not like it. Yes, Kevin. Okay. Okay. So sp3 hybridization is the Kevin's answer also. Okay. So I did not like it that all of you had given correct answer. All of you. How is it even possible? Okay. So that's why I kept a little bit of exception over here. Okay. I know all of you have got it sp3, but there is a slight exception that you have to consider over here. Look over here. Oxidation state +2. Okay. Nice. Then we have 4s0 3d. 4s0 3d9. Yes. Everyone. 4s0 3d9. Yes. 4s0 3d9. So 1, 2, 3, 4, 5. Then we have 4s. We have 4p. Then we have the 4d. Okay, then we have the 4d. Okay, now look over here. What happens is this is 3d, 4s, 4p, 4d. Okay, what happens is over here 9 electrons if I fill 1, 2, 3, 4, 5, 6, 7, 8, 9. Now NH3 is a strong ligand. Okay, NH3 is a strong ligand. So what happens is it has to do something to this electron. It does not leave it like that. Okay, now we cannot put electrons over there. Half electrons is not possible. We have a coordinate bond. So what happens to accommodate electrons? Your ammonia pushes the copper electron over here. Look over here. This over here. Okay, so this is an example, even though it is a strong field, but it is paramagnetic. Sarjana, it is paramagnetic, although it is a strong field ligand. So what will happen? Your 4 ligands will put electrons like this. 1, 2, 3, 4. Are you getting it, Kevin, Sarjana, and Kirtini? Yes. So hybridization over here, Jason, Kevin, the hybridization is what? This is your hybridization. DSP2. DSP2. Clear? Clear, everyone? DSP2, it is square planar. DSP2 is square planar. DSP2 is square planar. Square planar. Okay. And it is n plus 2 root n. Yes, it is 2 plus 1, 3 root 3. I hope it is clear till over here, everyone. Yes or no in the chat box? Is it clear? Is it clear? Okay. Just a minute. Just a minute. Okay, so we have got dsp2 hybridization, dsp2 hybridization. Okay, so now next, do it one more. Okay, then we'll go to next concept. We'll go to do this last question now. No exceptions. I'll not put any exception over here. Okay, just a minute. Okay, what example should I give you? Okay, do this. Do this. Fe CN6 4 minus. FeCN6 4 minus. Come on, do it. Then we'll do one question from your NEET exam. Okay, now the questions are actually very time consuming in this. They give you match the column always. Do this, then we'll do the NEET question, then we'll take a break. And again, I'm going to look at the books. Kirtini, just do not calculate oxidation state. You have to calculate everything. Okay, so we have got some hybridization. Very good, Jason. It is correct. Very good, Sarjana. It is correct. Very good, Anne. It is correct. Sindhuja has got it incorrect. Nice. I thought everyone will get it correct. So again, I have to give you something, some weird question to make everyone wrong. Sindhuja, how it can be sp3? You have 6 ligands, no? You have 6 ligands, Sindhuja. So how you can have sp3? At least you should have sp3d2. I can understand that. Yes, Kevin, I can see your book. Okay. You have the 6 ligand, no, Sindhuja. So how it can be sp3? Okay, fine, Kevin. You can keep it down. Very good, Bhuvaneshri. Sindhuja, try it again. It will be D2sp3. It should be D2sp3. You have a strong field ligand, Fe. Yes, Fe plus 2. What is the hybridization of Fe plus 2, or what is the electronic configuration? It is 4s0 3d6. So your 6 electrons will pair, Sindhuja. Your 6 electrons will pair. Yes. So you have the 3d, then we have the 4s, then we have the 4p. So your 6 ligand, Sindhuja, your 6 ligand will fill electron over here. 1, 2, 3, 4, 5, 6. Correct? So it is D2sp3. Is it clear, Sindhuja? D2sp3. Correct, Bhuvaneshri? Now D2sp3, just like a sp3d2, it is also octahedral. It is also octahedral. But since we are starting from D, we call it as inner complex. We call it as inner complex. We call it as inner complex. Acha, while typing, you missed D2. It is nice that if we do something, blame it on keyboard. How can you miss D2? I can understand we miss one alphabet. Okay. How can you miss D is at the one end, 2 is at the another end? It's like I do
No,
not
sir.
use.
Actually, my table is filled with books, sir. So while typing in.
Babre. So keep the books down.
Yes, sir.
Okay. You all talk like I do not use computer only. Yeah, I'm some 50-year-old, 60-year-old. Yeah. Is it clear, everyone? Is this clear? So let's do the. What about magnetic moment? You tell me, Sarjana. What will be the magnetic moment? Isn't it zero? Yeah. It is a diamagnetic, so magnetic moment will be zero because n is zero. Okay. So do this. Tell me the answer of this, the last one. Okay, then we'll end with the VBT. I'll give you all the possible example from the reference book. You can solve that at home. Okay, with the solution I will provide. Okay, come on, do this last one, then we'll take a break. This is the NEET 2021 question. Now, please do not attempt blindly. Check which one you'll get so that you have to do the less number of options. Okay, so if you look at B, look at the B, even C, B and C. Yeah, just a minute. Look at this B option. You got it? Acha, oh, we have done the first FECN 6.3 minus. No, FECN 6.4 minus we have done. FECN 6.4 minus we have done. As the break name, suddenly our mind becomes so active, no? By hearing the name of the break. Yeah? Let us do this quickly, so that we can get a break. Oh, FECN 6.4 minus. We have already done it. We already know the answer. I got it. Everyone will say D now. I get it. No need of writing that D in the chat box now. So the basic point is your 4 marks, your VBT question is done from the coordination compound. One question on the VBT definitely in the exam. Okay. Is it clear, everyone? Okay. So let's take a break. You take a break on time. It is 8. Let's start by 8:09. Please come back by 8:09. Okay. Do not too late. We have to complete the syllabus. Okay. Yes, everyone, come on back in the chat box. Yes, turn on your camera. Let us go to our next concept for the day. Come on, turn on your cameras. Sarjana, are we fine? Can we start? Anthony, and Anthony, why are you so late today? What is that unit from that match the following? BM. It is Bohr magneton. It is Bohr. It is done by Bohr, hence we give the name Bohr magneton. BM. Okay, Bohr magneton. Now, should I give you one more last question and then we move to CFT to show you what type of question comes? Okay, do this last one. Promise. Last question from VBT. Promise. Okay, last question from VBT. Then we'll move to CFT. Come on, do this. Yes, everyone, come on, solve this. D3sp2. Wow, Jason, that is not in the option only. D3sp2, how it is possible? See, that copper example was an exception. Every time it does not happen like that. Okay, Jason, every time it does not happen like that. See, when you have 6 ligand, no, there is only two options. Either one is sp3d2, yes, sp3d2, and the other is d2sp3. You will never have something like d3sp2. No, it is not possible. Okay, or sp2d3, not possible. Only two options are there when you have 6 ligands. Okay. And anyhow, B and C is already eliminated. Tetrahedral and square planar not possible with the sp3d2. Yeah. Okay, Sindhuja has got one answer. And Sarjana, shouldn't be a logical question. Shouldn't it be a logical question? You have a strong field ligand. Yeah. Yes, it should end over there only. Strong field ligand. Strong field ligand. It is a strong field ligand. So if it is a strong field ligand, Sarjana, Mn is what? Mn is 25. But we have Mn plus 3, so it is 4s0 3d4. 4s0 3d4. Okay. 4s0 3d4. Okay. Fine. See, Okay, I got it. Jason, why did you say D3sp2? I got it. See, first of all, D3sp2 does not exist, so forget about it. Okay. So whenever you have 6 ligand, no, remember this. You'll get explanation of this in CFT. Okay. Whenever you have the 6 ligands, no, your ligand has to start from over here. Okay, no matter even this, only this is occupied, fine, no issues. You have to start your ligand from over here. Okay, you'll get the explanation of this in your CFT. Okay, so remember this. So it is strong field ligand. See, simple thing is it is strong field ligand. The question gets over there only. Strong field ligand, obviously it will pair, it is D2sp3. Are you getting it, everyone? Yes or no? Sindhuja and Sarjana. Sarjana, you have not solved it this time? Is it clear? Okay. Shalom. Let us go ahead. Okay. Now let us move to CFT. Now there are few things your VBT failed to explain. There are few things that VBT failed to explain. First is we are considering too much of assumptions. Okay. Drawbacks. If you look at the drawbacks of VBT, that we are considering too much of assumptions. We are considering too much of assumptions. Okay, that everyone is at the same energy level, everything is going nicely, this is jumping over here, there. It does not happen like that. Okay, so we are considering too much of assumption over here, that okay, this is after this, this is after this, this is after this. So much of assumption. No, it is not like that. Okay, so many assumptions. Then the most important thing is it did not tell us about color. The most important thing, color. How do we get color? Yes, everyone. How do we the compound get a color? Why do your compound has a color? Jason, Sindhuja, and yes, due to what we see the color of a compound? Correct. DD transitions. Yes, there is a transition. Like when does a transition happens? When you are lower to higher and higher to lower electron jumps. Okay. Now over here, your VBT considers everything at the same energy. Each and every d orbital is at the same energy. So there is no DD transitions. Yes. Hence, the color we cannot see. The color cannot be explained via VBT. Obviously, compound is colored, but we cannot explain it via VBT. Is it clear? Okay. And also it does not, like we have seen so many exceptions. Yes. Weak field and strong field ligand, it does not differentiate between weak field and strong field. There are so many what we say exceptions. Yeah. Here till over here, everyone. Can we move to our next concept? That is crystal field theory. Crystal field theory, mark it important. From last 2 years, earlier this was not in the syllabus. Okay, this they never used to ask this, but from last 2 years they are asking a lot from this. Okay, crystal field theory, CFT. Come on, everyone is ready? Yeah, come on, give me yes. Forget about everything, forget about sleep. I want you to be active. Okay, I want you to look over here and understand this. Okay, can we start? Okay, CFT, crystal field theory. Now, the main thing, important thing was your VBT failed to explain the color. Jason, VBT failed to explain the color. So crystal field theory was developed from there. So crystal field theory assumed that simple. You have similarly you have d orbitals. Okay, you have d orbitals. Okay, now this is d orbital as the yes, and we discuss as the ligand approaches, what happens to d orbital? They go in the higher energy level. Yes, they go in little bit higher energy level. This is, let us say, energy excess. Okay, this is what is your energy excess. Okay, so what happens is they go in the little bit of higher energy level. Okay, now what happens is over here, as they go in the higher energy level, now ligand is approaching the metal. Okay, ligand is approaching the metal. So what happens is, as the ligand attaches to the metal, it splits into two. It splits into two. It splits into two. It splits into 2. This is what we call is a barycenter. Okay, this is what we call it as a barycenter. Okay, now this splits into 2. How? Three orbital get stabilized and go down in the energy. That is over here. We call it as T2G. We call it as a T2G orbital. Remember, T2G, 3 alphabets, 3 orbitals. 2 orbitals to stabilize that, it goes up. This is EG. Remember this. T2G, EG. Now, what are this T2G? What is EG? I'll explain you. This is what we are doing for octahedral. Okay, this is what we are doing for octahedral. I'm explaining it once again. Look over here. You have the D block elements. Yeah, your D block element, ground state, relaxing. So as the ligand approaches, what happens? They go in the higher energy level. Now, when the ligand finally attaches, the d orbital splits into 2. That is T2G and EG. 3 orbital goes down in the energy. 2 orbital goes up in the energy. Simple. Now, one which goes in the down in the energy and which one goes up. Remember this. Your D block orbitals, your d orbitals. Anyone know the name of the d orbitals? Yes, Jason, Sarjana, and do we know the name of d orbitals? Come on, tell me at least 2-3 names. Like there is some name for this orbital, there is some name for this orbital. Yes, Sarjana, we know that. Do we know? I know you have heard about it. I'll tell you, but and do you know? Jason, do you know? No? Okay, simple. Look over here. We have dxy. Yes, correct, Jason. dxy, dyz, dxz, dx square minus y square, and dz square. These are your 5d orbitals. These are your 5d orbitals. Okay, dxy, dyz, dxz, dx square minus y square, dz square. Now I'll tell you the trick how to remember and why such name is there. Jason, look over here. Sarjana. So we have 3 x's. Okay, x, y, and z. Okay. So what happens is these orbitals, no, they are in those plane. For example, Sarjana, if I have dxy, that will be in the xy plane. Okay, dyz, that will be in the yz plane. Okay, dxz, that is in the xz plane. Are you getting it, everyone? Yeah, that is in the plane. Then you have x square minus y square, it is on this axis. Okay, dz square, this is also on axis. So these two are on axis. Okay, these two are on the plane. Now, the one which is on the plane, we call it as T2G. The one which is on the axis, we call it as EG. Is it clear? And Jason, Sarjana, Sindhuja, Kirtini, Anthony, is it clear? EG, T2G. Okay. So the one which goes down in the energy, they are in the plane T2G. The one which goes up in the energy, they are on the axis EG. Now, why only T2G goes down in the energy and why only EG goes up in the energy? Look over here. What happens is the ligands in the octahedral, they are coming from the axis. Okay, your ligands are approaching the metal through the axis, and hence the orbital which are there on the axis, their energy increases. Are you getting it, Jason? The ligands are approaching to the metal via the axis, and due to that, the orbitals which are there on the axis, they become unstable. They go in the higher energy. That's why EG over here, A2G over here. Come on, draw this, everyone, and done in the chat box. Draw this. Draw this. Draw this. Come on. Come on, draw this and done in the chat box. I hope it is clear. Easy, no? It is easy. It is easy. Yeah, it is easy.
Sir? Sir?
Yes, Mr. Anthony.
Sir? Sir, can you explain the plane again, sir? I couldn't get it.
Plane. What plane?
The plane thing, dxy, dyz, and dx.
Okay. And Anthony, why did you join so late today?
Sir, I went to hospital and that time only I came, sir.
Why? What happened?
Sir, like I was not feeling well, sir. So
You
I
went to the
was,
hospital directly. No
yes, sir.
clinic, direct to
Le-
ICU.
No, sir, no, sir. Like it was clinic only, sir. Like small
Ah,
hospital,
thank God. Okay.
hospital like clinic only, sir.
Okay. I thought that you ran with the oxygen mask and all that, and so much of dead patients that you have come back. Oh, yeah. We exactly cough at the time when someone asks about our health, isn't it?
No, sir. Seriously, sir.
I was not well.
Sir, sir, like past 2 weeks I am
Ah.
suffering from this, sir.
Acha, okay. No, I'm not joking. Okay, it is fine. You will be fine. Don't worry. And do not eat something from outside. You all eat this Manchurian and all from your schools. Do not eat that. Okay, do not eat oily food. Okay, in the
Okay, sir.
end, during exams. Come on. I'll tell you what is this plane and axis. Okay, look over here. Anthony, we have 5d orbitals, correct? So 5d orbitals, each orbital has a name. Just like Anthony has a name, okay, each orbital has a name. Okay, so the name of the orbitals are xy, yz, xz, x square minus y square, and dz square. These are our name of 5 orbitals. Now, I am telling you why is that name. For example, Anthony, turn on your mic. Why your name is Anthony? Yeah, turn on your mic.
Sir,
Why your name is Anthony?
sir, I don't know, sir.
Why did your parents keep your name Anthony? You have to find it out.
Okay,
Yeah?
sir.
Okay, fine. So, just like you do not know about your name, but we know about the orbital name. Okay, we know about the orbital name. Why their name is XY, YZ, and XZ. Okay, we know about their name because this XY, YZ, and XZ, no, these are the planes. If you look at the axis, yes, and if you look at the axis, we have X, Y, and Z axis. So this DXY, it is in the name. That means what? XY. That DXY is in XY plane. Now, where is XY plane? Over here. Okay, this is X axis, this is Y axis. So this is your XY plane. Your orbital is in the XY plane. Then we have YZ. That YZ means this plane. This is in the YZ plane. Then XZ, that means X axis, Z axis, in between them there is a plane. Okay, that is why we call it as plane. Then we have the axis. So x square minus y square. So you have orbital on this axis. Okay. Then we have dz square. That means the orbital is on this axis. Are you getting it, Anthony? Is it clear? Is it clear, Anthony?
Yes, sir.
Okay. Just a minute, everyone. Just give me. Is it clear, Anthony?
Yes, sir. What is that T2G, sir?
Ha, so the name together, okay, together we call them as T2G. Okay, together we call them as T2G. The group of these three, they are together. Okay, these are on the plane and they are together. So we call them together T2G. Okay, their group, they are on the same energy. The one which are in the planes, they are in the same energy. Over here, I have drawn the energy axis, correct? So this T2G, they are on the same energy. You can see I have drawn them horizontally. Yeah, they are on the same energy. And 2 EG orbital, the one which are on the axis, they are on the same energy. But those two, there is a difference between those two, and that we call it as a del O. Okay, delta octahedral. Or we also call it as 10 DQ. Or we also call it as 10 DQ. Just a minute, everyone. Just give me a minute. Okay, so this difference between T2G and EG, the difference we call it as del O or 10 DQ. Okay, those are just the name. Okay, those are just the name, 10 DQ and del O. Now you can see the lower T2G and this barycenter, the difference is small. Sarjana, look over here. Jason, the difference between barycenter and T2G is small. Okay, and the difference between barycenter and EG is large. Okay, so this difference is the one which goes in the higher, we call it as 0.6 plus 0.6. Okay, and this is minus 0.4. Okay, plus 0.6, write it down. The difference between EG and barycenter, there is a use of it, I'll tell you. Okay, but write it down now. The difference between barycenter and EG is plus 0.6, and the difference between barycenter and T2G is minus 0.4. Is minus 0.4. Minus 0.4. Come on, write it down. And okay, now look over here. Look over here. How to do this and what is the use of CFT? What is the use of CFT? Chalo, let us do the CFT. Is it clear? No, everyone is clear till over here. Yes, everyone is clear till over here. Jason, Sarchana, and what is barycenter? Barycenter means the d orbital, the energy of d orbital. Okay, this is your d orbital after coming higher in the energy. The ligand, originally your d orbital is chilling. Okay, originally your d orbital is chilling. Okay. Now, as the ligand approaches, it goes higher in the energy. It goes higher in the energy. And that energy, before splitting, we call it as barycenter. Okay, that is the energy of the d orbital. Are you getting it, Sarjana? Okay. So, from the barycenter, how much it has split? That is what your barycenter means. That is what your barycenter means. Is it clear now? Sarjana, can we go ahead? Okay. Shall let us go ahead now. Let us do some CFT questions. Let us do some CFT examples. Okay, let us do some CFT example. Yashadeep. Yashadeep, I'm audible. Ganesh, I'm audible. Ganesh. Ganesh, I'm audible.
Yes, sir.
See, there were 2-3 students, for example, Kevin. Kevin was there in the session, but after some time he left. So kindly call his parents and ask no. Why did he left? Okay,
Yes, sir.
thank you. This is the nice way, no? I enjoy it. Yeah, I enjoy it. Kirtini, I enjoy it. Call their parents. Shouting. I'm 100% sure that his parents do not know that he has left the session. 100% sure. See, he'll join in 5 minutes. Just wait and watch. I'll tell you, he will join in 5 minutes. Let's wait. Okay, let's wait. Let's see after 5 minutes. Okay. Chalo. Let us do our example. Can we go ahead? After he comes back, we all will make fun. You all will make fun of him. Let him come back. Okay. Chalo. Let us go ahead. Now let us say I have some complex. Okay. I have some complex. Okay. In that my configuration is D4. Okay. My configuration is D4. I have a complex, any copper complex, manganese complex, whatever it is. Okay. After oxidation state, I have D4. Okay. I have D4. Okay. D4. Now over here, I want everyone's focus important. Look over here, Jason and Sarjana. Important. D4. Okay. So what has happened again? Ligand has approached, gone higher in the energy. Then what happened? It split. It split into two. That is T2G and EG. That is T2G and EG. T2G and EG. Okay. Now you have to feel those electrons, Jason and Sarjana. Look over here. You have to feel those electrons. Okay, D4. Okay, D4. So what has happened in the D4? Let us say we have two. Okay, Ganesh. We have two ligands. Let us say we have two ligands. We have two conditions. Okay, we have two conditions. I'll consider both of the conditions. Okay, imagine we have a d orbital over here. Okay, T2G EG. Okay, T2G EG. Okay, so let us say we have two conditions. One, we have a strong field ligand. Wow, Kevin has joined. I told you, no, he'll join in 2 minutes. One is a strong field one is a weak field. Yes, Mr. Kevin. Let's hear what excuses giving.
Yes, sir. Hello.
Hello. Oh, hello, Mr. Kevin. What happened?
Yes, sir. Yes, sir. Login ID expired.
Oh my God, login ID expired from
Yes,
last
sir.
20 minutes.
No, sir. I was actually trying to
Ah.
enter and so on.
But
Really,
how come like after call in 2 minutes your login started? Yeah, yeah. What? In 2 minutes after call your login started? Yes, Kevin?
Yes, sir. I was actually trying to log in only, sir, so far.
Okay. I guess you have got good shouting from your dad. Yeah? Your face shows it. It is fine. Chalo. Anyways, I am sorry to do that, but I was just checking what happened. Where did you go? Okay? Okay. You got good shouting. Kevin, it is fine. I'm sorry. I apologize. Okay? I just wanted to inquire about you, like where did you go? That's it. Okay? Come back, everyone. So our mission accomplished. Kevin is back. Okay? That does not mean that you want me to talk to your parents, so you will leave the session. Yeah, it is fine. Okay, look over here. Everyone come back. So we have D4, we have D4, D4. Okay, two cases we are considering. Jason, Sarjana, we are considering two situations, and one where we have a strong field ligand, one where we have a weak field ligand. Okay, one where we have a strong field ligand, and where are you looking at? Look over here. One is where we have a strong field ligand, one where we have a weak field ligand. So what will happen? Strong ligand, Jason, it is strong. It is like me. Okay, it is strong. It is like me. Just like how I have power. Yeah. One called Kevin is here. Yeah, I am strong. Isn't it? Kevin, I am strong. Isn't it? So we have a strong field ligand like me. So what will happen? That will split those orbitals more. That will split those orbitals more. Now due to that, when I feel this 4 electron, Jason, Sarjana, when I feel this 4 electron, Kevin, look over here. I have called you, so I'll explain you once again. Don't worry. Okay. So 4 electrons, it feels like this. 1, 2, 3. Now 4th electron, since the gap is very high, due to strong field ligand, the 4th electron will feel over here. Are you getting it, everyone? Jason, Sarjana, and are you getting it? The 4th electron will fill over there due to the strong field ligand. Okay, due to the strong field ligand. But when you have a weak field ligand, 1, 2, 3. So in the weak field ligand, we say that your delta O is less. The size of delta O is less than the pairing energy. Okay. So what happens is the 4th electron, it jumps on top because the difference between your pericenter, the T2G and EG is not that much. Although the values are same, understand this, Jason, Sarjana, and Kevin, the values are same. Okay, it's split by equal value. This is minus 0.4, this is plus 0.6. The value is same, minus 0.4 plus 0.6. But due to strong field and weak field, what happens? The electron pairs over here, the electron goes over here. Is it clear, everyone? Sarjana, Jason, and is it clear? Is it clear? Okay. Now, Kevin, I'll explain you once again. Those who have not understood, I am explaining once again. Mr. Anthony, are you there? Even Anthony is gone. So let us call back Anthony. Yeah. Anthony, are you there? Ganesh? Today is a nice day. Ganesh? Let's do a phone a friend once again. Ganesh? Ganesh? Are we there, Ganesh? I guess I have to call the Ganesh parents now.
Yes, sir.
Ganesh?
Yes, sir.
Kindly call Anthony. He has left
Okay.
the session.
Okay, sir.
Okay. Okay. Anyways. Okay. Come back. So strong field and weak field, pairing and no pairing. Okay. That is how you have to solve it. Anthony, Kevin, I'm explaining once again. Come back serious. So what we have, Kevin, CFT. In the CFT, we have everything at the same energy level. Okay. As the ligand approaches, your d orbital goes higher in the energy. As ligand attaches, your d orbital splits into two. That is T2G and EG. So this 3 orbital are your T2G, which goes down in the energy. These orbitals are EG, which goes up in the energy. Okay. So you get T2G EG. So if you have a strong field, the electrons will pair. If you have a weak field, the electron will go up. Is it clear, Kevin? Yes? Okay. Now we have something called a CFSE. Now again, CFSE. Okay, this CFSE, okay, crystal field stabilization energy. Till last year, this was not asked. This was considered, Jason, as an advanced topic. Okay, JEE advanced topic. But from few years, last year itself, they have asked. I remember CFSE, last year they have asked, so you should know how to calculate it. Okay, simple, nothing like advanced, something is there, it is very simple. Okay, what you have to do, Sarjana, you have to count the electrons. Okay, simple. Over here, how many electrons are there in T2G? 4 electrons. So minus 0.4, we have 4 electrons. Okay, plus nothing in EG, so 0. Over here, minus 0.4 into 3 plus 0.6 into 1. Are you getting it, everyone? Are you getting it? Wow, Anthony is back. Are you getting it, everyone? Yeah. So over here, this will become minus 1.6. Yes. What will be the value of it? Calculate. 1.2 minus. So this will become minus 0.6. Yes. This will become minus 0.6. Are you getting it, everyone? Mr. Anthony. Yes, Mr. Anthony. Turn on your camera and mic.
Sir?
Yes, Mr. Anthony. Where did you leave?
Sir, I'm here only, sir.
Oh, again cough? Oh my God. What happened? Why did you leave the session?
Sir, I
Login
was here
issue.
on... Yes, sir.
Are you sure, Anthony?
Sir, seriously, sir.
What, you were here?
Yes, sir. I was in the class only, sir. Like, I gave the refresh button it asked, so it went...
Oh my God. Anthony. What? See, it is fine, but you can be honest to me, yeah? Okay, chalo, no issues. I assume that Kevin's login ID expired, Anthony's refreshed, and it directly gone out for
Yes, sir.
10 minutes.
Yes, sir. Login issues only, sir, for me.
Okay. Login issues. Fine, I take that. Chalo. But stay, do not leave, okay? It's
Okay,
nice, no? It's nice weapon I have. New weapon I have found. Nice. I love it. I'm loving it. I'm loving it. And you know, the best part is, as soon as the call goes, after 2 minutes, there is no login issues. Yeah. But till the call does not go, there is a login issue. Nice. Okay. Is it clear? Minus 1.6, minus 0.6. How to calculate the CFSE? Is it clear? Okay. Can I give you one more? Will you tell me CFSE for that? Can I give you one more? Will you tell me CFSE for that? I'll give you one more example. Suppose I have, let us say, suppose I have D4 we have done, no? Let us say we have D6. Okay, we have D6. Okay. I want CFSE for D6 for strong field as well as weak field. Come on, calculate and draw the CFT. Draw the splitting. I want to see the book. Okay. Draw the splitting. Anthony, for you, I'm keeping this page open. For you, I'm keeping this page open. See, this is strong field, this is weak field. Okay, so 6 electrons you have to fill it in this orbital, D6. Okay, you try it with this method. Okay, I have kept this page open for Anthony. So D6. Okay, then you have to calculate the CFSE. The value over here, Anthony, I'm explaining once again just to you. Please do not leave the session. Okay, so the value of the below orbital is minus 0.4. The value of the above orbital is plus 0.6. Okay, so you have 3 electrons, 4 electrons over here. So 4 into minus 0.4. Okay, no electron over here. So plus 0. So total value you have got this. Okay, in the second case, in the weak field, the 4th electron jumps over here. Okay, so what happens? Minus 4 plus 6. So minus 4, you have 3 electrons over here. So minus 4 into 3, sorry, minus 0.4 into 3 plus I have 1 electron on the top. So plus 0.6 into 1. This is what I have got. Okay, so similarly, Anthony, you have to do it for D6. Come on, everyone, tell me CFSE for strong field, weak field, both of them for D6. Okay, Jason had got it. Jason, not SFSE. It is crystal field stabilization energy, CFSE. Okay, very good, Jason. Very good, Sarjana. Both of you are correct. Yes, Kevin, I'm waiting for your answer. Very good, Anne. Easy, no? Very good, Kevin. क्या बात है? Kevin, which one? But minus 0.4 for strong field or weak field? Very good, Sindhuja. Nice. Everyone is giving the correct answer. Wow. Nice. Okay, and remember this, everyone. This minus 1.6, okay, we can write it also as minus 16 dq. If we are writing dq, that is in term of this also we can write. Okay, minus 0.6, I can also write it as minus 6 dq. So remember, does not change the meaning. It is still minus 0.6. It is still minus 0.6. dq is just a unit that we multiplied by 10. Remember like that. Okay. Done, everyone? Hope everyone is clear. Very good, Kevin. Okay, so for D6, minus 2.4. For weak field, you'll get minus 0.4. Very good. Nice, 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 nice. Nice. Okay. Shalom. Let us go ahead. Yeah. Let us go ahead. And this again, I'll repeat, this is also minus 24 dq1 and the same. This is minus 4 dq, one and the same.
So
Yes,
you can
Anthony?
create it like high spin and low spin also.
That is where I am coming to next, Kevin. That is where I am coming to. Okay. So is it done, everyone? Clear till over here? Okay. Now look over here. Minus 24 dq and minus 4 dq. This is what you have got. Now there is one more term that you will come across, is the high spin and the low spin. Okay, is the high spin and the low spin. Okay. So for example, you had D6. Okay. In D6, okay, there is something called as, like in general, everywhere there is something called as high spin and low spin. I'll write it opposite. Low spin and high spin. Okay, low spin and high spin. Look over here, everyone, Sarjana. Low spin and high spin. So low spin and high spin, what is it? Okay, it is kind of alternative name for your strong field ligand. Okay, I'll tell you why. Wait. Oh. Strong field ligand and weak field ligand. Strong field and weak field ligand. Why? Look over here, Jason. D6. So how did we fill the electrons? Anthony, we have two T2G down, EG at the top. Okay. So in the strong field ligand, you have filled the electrons like this, isn't it? 1, 2, 3. Then fourth electron did not jump up. It paired over here. 4, 5, 6. Yes, everyone got this? Yes, Arjuna? So over here, everything is paired. Jason, everything is paired over here. So that means there is no spin. I hope everyone knows that electron is continuously spinning. It is in the plus half and minus half. They both cancel each other, become 0. Are you getting it, Jason, Sarjana? Yeah. So there is, Kevin, there is no pair, no unpaired electron. So for that we call it as low spin. For that we call it as a low spin. That if there are less number of unpaired electron, low spin. High spin, for example, D6, what you have done over here in the weak field ligand. Okay. So how did your 6 electron enters? 1, 2, 3, 4, 5, 6. Are you getting it, Sarjana? This is your high spin because you have 4 unpaired electrons that are continuously spinning and no one is cancelling that. Is it clear, Anne? Is it clear, Kevin? High spin and low spin. Yes, Induja, Jason, clear? Jason, are you there with us? Yes. Okay. Weak field, strong field, high spin, low spin, done. Okay. Let us do the last concept for the day. Then we'll do the class assessment. Okay. Last concept for the day. Then I'll stop. Don't worry. Okay. No, I have to do one more. Okay. Look over here. Then we have something called as tetrahedral. This what we have done, yes, was for your octahedral. Whatever we have done was for your octahedral. Yes. So mention it over here. So just like I have mentioned it over here, if you remember, whatever we have done was for octahedral complexes. Okay. For your octahedral. Now what for tetrahedral? Tetrahedral is opposite. Okay. Tetrahedral is opposite. What do we mean by that? In the tetrahedral, the splitting is opposite. Okay. Your d orbital as it is, d orbital as it is. Okay. Same logic goes up. But in the tetrahedral and Sarjana, Jason, the ligand approaches via the axis. The ligand approaches via the axis. So hence what happens is your Eg comes down and T2G goes up. T2G goes up and Eg goes down. Are you getting it, everyone? Eg comes down. Okay. It comes down by minus 0.6, goes up by plus 0.4 for tetrahedral. Okay. For tetrahedral, it goes down by minus 0.6 and goes up by plus 0.4. It was opposite. Everything was opposite in octahedral. Yes. And this difference will always be smaller than the octahedral. This delta T, we call it as delta T also. This tetrahedral splitting will always be less than octahedral. How small? Please write it down. Delta O will always be smaller than delta T. This is the relation. This question has also come. They had given the value of delta T and asked us delta O. So write down this relation. Your delta O, okay, will always be, just a minute, did I write opposite? This should be delta T. Delta T is always smaller than delta O. Delta T is always smaller than the delta O. Okay, by 4 by 9. Write down this. Delta T will always be smaller than delta O. So this question can also come in the exam. Is it? Come on, write it down and done in the chat box, everyone. Done. Okay. Now the last one, look at the diagram. Okay, I'll tell you about the square planar. The last one. We have done octahedral, tetrahedral. Now the last about square planar. Okay, in the square planar, you do not have to fill any electrons. Okay, look over here. And by the way, if CFSE comes over here, Jason, you have to solve everything as it is. Okay, what we have done for octahedral, you have to do it for tetrahedral also. Okay, whatever we have done for octahedral, you have to do it for tetrahedral also. Okay. Now come on, the last one. Look over here. The last one. Now look at this diagram. Look at this diagram. Yes. So over here, yes, Jason, look over here. Over here we have d orbital. Okay, on the left hand side. I'll zoom it in a little bit. We have a d orbital, as I told you. What happens as the ligand approaches, they go higher in the energy with the average energy. Correct? Then in the octahedral, Sarjana, Jason, and what happens? They split into two. T2G goes down, EG comes up. Okay. Now from octahedral, we are forming a square planar. Okay. How does your octahedral look like? Your octahedral looks like this. Yes, Jason, why do we call it as octahedral? Yeah, Sajna and Jason, Kevin, why do we call it as an octahedral? Yes, what is octa? What is the coordination number? Come on, tell me. What is the coordination number? What is the coordination number of metal in octahedral? Yes, what is the coordination number, Sajna? Jason? Very good, Jason. The coordination number is 6. So what is this octa in this? Yeah, what is 8 in this? Okay, so if you notice, Sarjana and correct, Jason, if you notice that if I join this, yeah, one side, if I join this right hand side, second triangle, back third side, and on the left hand side there is a fourth side. So 4 triangles we are forming. So 4 triangles on the top, 4 triangles on the bottom, 8 triangles and 8 sides. Are you getting it, Sarjana, Jason, and Kevin? Yes. That is why we call it Anthony. That is why we call it as octahedral. Sindhuja, is it clear? That is why we call it as octahedral. Okay. Now what happens is, if I have to form a square planar, okay, if I have to form a square planar, how I will form a square planar? I will just remove this ligand. I will remove this ligand. I have got my square planar. So what I have done, I have removed the ligand from the z-axis. Jason, what I have done, I have removed the ligand from Sarjana. I have removed the ligand from the z-axis. So due to that, what happens? Whatever orbitals on the z-axis were present, there is no ligand near z orbital, they get stabilized. Okay, whatever orbitals, Sajna and Jason, present at the z orbital, Kevin, they get stabilized. What happens? Stabilized means what? Over here, your z, for example, in the T2G, we had, Kevin, we had dxy, dyz, and dxz. So wherever the z plane is no, they will get stabilized. Okay, so from T to G, your Z has come down. Wherever the Z is stabilized. Are you getting it, Jason, Sajna, and are you getting it, Kevin, Sindhuja? The one with the Z is stabilized because we have removed the Z axis. So it came in the lower energy. But one with the XY has gone up now. Yes? You have to focus on this too. Yes? The one with the Z has gone down in the energy. The one without Z has gone up. Similarly, in the EG, what we had? In the EG, dx square minus y square and dz square. Correct, Jason? In EG, we had dx square minus y square and dz square. So again, the same thing. dz square come over here, even more stable than dxy, and dx square minus y square on the top. Clear? And Sarjana, Jason, Kevin, Sindhuja, Anthony, clear? Everyone? Okay. So over here, this has come once in the exam. This is your energy level. So the one with the highest energy level is dx square minus y square. Then we have dxy. Then we have dz square. Then we have dxz is equal to yz. This is for square planar. Come on, write it down and done in the chat box. Come on, write it down. I hope everyone is clear with it. Write it down and done in the chat box. Come on, write it down and done in the chat box. Okay.